All right, it's about time, 2 o'clock in the afternoon. Thanks for returning from your lunch break and staying with us for the next 30 minutes. My name is Andreas Hildebrand. I'm working for ALC Networks out of Munich. And we are the guys who invented the Ravenna audio over IP technology. So the next 30 minutes is about all relevant standards to this particular audio over networking industry. So if you haven't heard about any of those standards, this presentation will give a good overview on what is relevant to audio over IP in a wider view. So first of all, of course, we have AES67 as a standard, which defines the high performance audio over IP interoperability. Then next we have the SMPTE ST2110 suite of standards, including the SMPTE ST2059, which basically cover the elementary essence data transport on managed IP networks. So the same what AES67 is for audio is 2110 for media, for video, audio, and ancillary data, so for the video production guys. Then we have the Advanced Media Workflow Association with the set of NMOS standards. Well, I wouldn't call them standards, but technical specifications, which enhance or accompany the AES67 and 2110 standards by defining upper layer operational and management functionalities. Since we are in the AES here, AES70 is also part of the game, which is a device control and connection management protocol. And most currently we have the audio metadata transfer working group, which defines a standard for transporting real-time transport of audio metadata, just the way they did with AES67 for linear audio data. So that's the scope which I'm touching on today. And let's jump right into AES67. What was the original goal of AES67? Well, to provide a method to interconnect a variety of already existing IP-based networking systems. So naturally AES67 is an interoperability standard, and it is it's purely based on existing protocols and trusted IT standards. So the idea was, by doing this, to have a high acceptance by the existing manufacturers of solutions to adopt AES67 and to finally being able to provide a wide range of interoperability. Here's another view to the problem statement we had before we were developing the AES67 standard. We had these variety of different audio solutions, which each on its own provides simpler and better connection between audio equipment. If you take your Dante or your Ravenna or Q-Line equipment, the problem was they don't interoperate with each other. This is a different view of the same problem. We have these existing audio over IP standards. They're all based on IP. They don't talk to each other, at least not based on IP, right? So except for Livewire and Ravenna, which were able to talk to each other since 2012. And AES67 then was the goal to define interoperability requirements, which, if they are adopted by these technologies, would enable the direct interchange of media based on the IP network without having to go through analog, digital, or any other means of signal interchange. So the status of AES67, I won't explain the details of AES67 in this presentation. The status of AES67 is the initial publication happened in 2013, just in time for IBC. After 3 years of work, we had at times up to 100 participants in the task group, in the working group, consisting of manufacturers and consultants, system integrators, end users. So even from the radio stations, we had quite a good participation. So that at the end, the standard actually was able to cover all the professional audio applications, or is at least suitable for all the professional audio application, and not just for broadcast or recording or installed sound, but basically for all of them. In 2015, we saw the first revision, which basically contained a corrigendum and clarifications. We had full backward compatibility, so we didn't change anything which would break the original definitions. It was more about removing some ambiguities and removing some apparent errors. 2018, we had the second revision, the latest revision of AES67. Further clarification have been added, and most important, a so-called PIX has been added. So this is not something you can eat. It's the Protocol Implementation Conformance specification? No, not specification. What is it? Statement. Just a statement. Protocol. So basically this is a lineup of all the requirements. The standard lines up or defines a nice lineup one by one so that manufacturers can tick the checkboxes and say, okay, I'm compliant in this and this and this and this and this respect, and I'm also compliant to these and these and these options. Oh, and here's one feature I'm not supporting from the standard. The benefit is that then system integrators as well as end users can look to these PIC specifications and see if the devices they have in mind actually match their application requirements. So the current status of AES67 is we just had a meeting yesterday in the working group. We identified further topics which need further work, further clarification, further homologization also with the SMPTE 2110 standard. And so there is something in the work, and we will definitely see a next revision of the AES67 standard maybe by the end of 2020. We just started on a number of tasks, and if we are as fast as we have been in the past, we will see a new revision in 2020, again without, and that's absolutely clear, without breaking any of the existing compatibility. So anything which is in 2013 will still hold in the 2020 revision. So it's a well-maintained standard. We are still working on it. Further work within the AES task groups. I mentioned AES70, which is an open control architecture. So a device control protocol addressing the configurative needs of audio devices. We have heard several presentations on that topic today and throughout the days. That has been initially published in 2017. Basically, it was taken from the OCA Alliance, that's why it's Open Control Architecture, and received, after some revision work, the AES stamp. And in 2018, that group published a revision with further improvements and additions. For example, WebSocket UDP support, CM3 definitions, and they are currently working on further improvements as well as on AES70 connection management for AES67 streams. And the latest task they added to their scope of work is NMOS convergence. So they are looking into letting AES70 principles being controlled by NMOS specifications, so that NMOS and AES70 can work hand in hand. And I will come to NMOS a little bit later here. Another interesting work was the X238 initiative. They were putting out, or they are to put out requirements. So it's just a requirement document for media network directories and directory services. So in other words, if people are developing directory services or network directories, they are setting forth technical recommendations what these services should cover. For example, registration, query, administration protocols, what also everything which is lined up here. So that is an interesting document. It's not a standard like AES67 setting forth some technical details, but some important recommendations from the point of view of the audio industry with respect to upper layer functionality. The latest project we have is the X242 in this realm. Of course, AES has much more projects, but the latest one which applies to audio networking is streaming audio metadata over IP. So why would we want to do this? We can already stream audio metadata over IP by using AES3 encapsulation. The SMPTE 2110-31 standard covers anything AES3 can transport, so metadata can be part of this. But we have application, particularly in the immersive audio field, where we want to have larger volumes of metadata accompanying the audio objects, and also tighter timing relationship and more flexibility. So we are looking into defining a mechanism of transporting real-time audio metadata, just the way we did for AES67 for linear PCM data. So that work is currently going on. Interestingly enough, SMPTE 2110 has also set up a group which is covering the very same topic. It will receive the -41 number. So both groups are currently working, and we are seeking alignment between these two groups so that we don't end up with two different standards. Just the way we found a nice alignment between -30 and AES67. So we have already been spoken about 2110. We've mentioned that, so let's look what 2110 has in the back for us. It's a series of documents which basically specifies the transport, synchronization and description of separate elementary essence streams. So video, audio, and ancillary data are now transported as individual essence streams on the network. Not any type of network, not the internet. It's for well-managed IP networks. And the primary application case would be professional production environments. So anything where broadcast content is produced in studios or large sport events, things like that. It's not for distribution of these of content over the internet or any other wide area connections. Basically, why are we doing this? Basically, there are two fundamental approaches to IP transport. One is the bundled approach, where the audio, video, and metadata is a multiplex signal or a multiplex content which travels coherently in one stream. The benefit is everything is nicely in place, and if you receive that stream, you get all the content. The disadvantage is if you just need to work on the audio data or the ancillary data, you have to receive the whole content, have to de-embed it, work on it, and potentially also re-embed it again. So that's where 2110 kicks in. 2110 is the essence-based approach, where the individual essences are individual streams on the network. So if a receiver is only interested in the audio, he can just subscribe to the related audio stream, do the audio processing, and reinsert another audio stream to the network without having to deal with a large volume of video data. Of course, this all has been taken care of in terms of synchronization. You will see in a minute how that works. Here's another illustration describing the differences. First of all, here again, there's the typical SDI signal raster. We have the active image area. We have the ancillary data space, where traditionally also the audio data had been transported. And by separating these data from each other, we can also save a lot of bandwidth, particularly with the blanking intervals we have in the SDI video, because we are only transporting now the active video part. So we are skipping all the horizontal, vertical blanking, so that the video data rate, the video data amount is decreased at a significant value. So that is basically that view on 2110 again. And here's the difference between the already existing 2022-6 mechanism. We have a multiplexed data stream in 2022-6, where, as I explained, if you want to work on the audio, you just have to receive the whole stream, de-embed, process, re-embed, and send off another volume stream. And that's this part of the picture. And in 2110, we have individual streams from the very beginning, and you only have to receive that data which you're interested in processing it. So that's again the difference between these two existing schemes. Now 2110 is not intended to replace 2022-6. 2022-6 will still be needed whenever it comes to finally distributing the content through wide area network links. That is not the realm of 2110, that's the realm of 2022-6. So let's have a closer look into the documents. 2110 specifies the -10 document is defining everything which is related to synchronization and the transport layer and everything which is agnostic to the media itself. The -20 touches on the payload format for uncompressed active video. 2110 instructs people about the traffic shaping for this uncompressed, for this high volume uncompressed video traffic. You can imagine if we would try to send out the huge amount of video data from one frame of video just back to back into the network, that can easily overload some of the subsequent buffering stages and switches, or even the end nodes. So they had set out a traffic shaping requirement, which would evenly space the video RTP packets so that subsequent stages do not get overloaded by a bunch of packets they see back to back coming in all together. That is just for the video side of things, because we are dealing with very high volumes of data there. For the audio side of things, we have the dash-30 document defining the PCM digital audio payload, which basically is the same as this defined in AES67. We have the dash-31 document, which covers the AES3 bit transparent transport. Remember, AES67 is linear 24-bit PCM only. AES3 has additional metadata bytes which cannot be transported with AES67. So we had to define the dash-31 document. And while dash-30 is based on AES67, SMPTE found that the existing Ravenna AM824 specification is perfectly for transporting AES3 bit transparently. So they took up the Ravenna specification, AM824 specification, and that is the dash-31 standard now. Dash-40 is then the standard for the ancillary data of the SDI signal, so that we have these three different essence streams. Let's have a closer look at the linear PCM audio transport. Basically uncompressed audio based on AES67. It's relatively flexible. You can do 48, 96 kilohertz, 1624 bit depth. You have variable packing time for the individual packets, and the channel count can be anything up to 64 channels in 2110-30. However, the only mandatory subset or formatting subset is identical to what AES67 requires. So, in other words, these various conformance levels we have in -30, in SMPTE 2110-30, only level A is the only mandatory level, and that's the one which is identical to the mandatory requirements of AES67. You can do more than just AES67, but the only mandatory requirement in the overlap with AES67 is the conformance level A. So that is AES67. If we look into details, we will see that -30 and AES67 are not absolutely identical. -30 is specifying some constraints. If we look at a more general picture here, we can identify that SMPTE 2110-30 with level A and level B are subsets of the specifications of AES67, with the exception that a few things have to be considered by an AES67 device in order to fully be 2110 compliant. So another view would be like this. We have AES67 and 2110-30 as a subset of AES67, and we have a few constraints which are outlined in -30. However, these constraints have by now been implemented by all AES67 implementations. So the implementers have managed to cope with these constraints which are in the -30 standard. So we have then -31, the AES bit transparent transport, which can basically transport not just audio with the metadata, but anything which can be encapsulated in AES3, including non-PCM data, according to SMPTE ST337. And the way we do it, as I already mentioned, we build it on Ravenna's AM824 format, which has everything which AES67 is doing. The only difference actually is that instead for using just 3 bytes for the PCM part of the audio, we use now 4 bytes. We add 1 byte for the AES3 metadata, PCUV bits plus block and frame start. And that is the only difference. Of course, we have to signal this difference to the receiver in the SDP, while the AES67 format would look like L24 at 48 kilohertz, and then the channel number, the AES3 data or the -31 would signal AM824 with 48 kilohertz and number of channels. Every other SDP parameter is absolutely the same, so this is really not a new specification or new invention. It's just adopting this payload format by adding 1 byte and signaling the specifications. So if we look at the compatibility again, now since AES67 does not cover AES3, AES67 is out of the game, but Ravenna is fully in the game, Ravenna being fully AES67 compliant, as well as 2110 in that respect. Well, no wonder, it's the payload format being taken from Ravenna, right? So, there's further work in development in 2110. We have the -22 document, which covers the transport of constant bitrate compressed video. It's not specifying a codec, it's just specifying the way constant bitrate CBR content is transported. So you can use TICO, VC2, J2K, and all these type of codecs can be used with 22 document. We have the 23 document. If we have higher bitrate streams like HDR or 4K or even 8K or high frame rate motion capture camera streams, they probably don't fit into the physical constraints of a given interface. Let's say a 10 gig interface, they probably need 40 gig for transport. So in order not to require a 40 gig interface, that work group is currently defining the way how these signals are split into lower bandwidth signals as valid -20 streams. So they just define how these signals is decomposed into valid -20 streams and how they have to be recomposed on the receiving end so that it can travel on lower bandwidth links. So they are on its own valid -20 streams, just with less data in it. And since there are multiple of these streams, they can be recombined to the higher bandwidth, higher data content original stream. That's the -33. A 23 document. Then the 41 is what I mentioned earlier, is the parallel development of the X242 metadata standard. So they cover the very same task, transporting any sort of real-time metadata, and we are in the process of aligning the work between AES and SMPTE in order to not get two different standards. Further work which is currently going on in the 2110 group, we have a 1-year review. Remember, the documents had been published in 2017, so we are currently in the process of the 1-year review. Also new work is going on in -24. We have the definitions for standard definition video, and also a PIX is under development for 2110, just the same way we did it for AES67, you know, lining up all the individual requirements in a PIX document so that manufacturers can check and make their tick the boxes for that, sorry. Then the related standard 2059 is about the PTP profile. Again, this is a published standard, but they also in a 1-year review. So they are also looking into enhancements, clarifications, removing ambiguities and these kind of things. Another group is addressing 2059 security as well as PTP monitoring recommendations. This is currently going on. In a related standard groups, the VSF, the Video Services Forum, is currently addressing how to transport 2110 signals over wide area network links, not the internet. That cannot cope with that. And we also have a 2110 format enumeration, which I don't want to give any details on right now. And finally, it's interesting to know that the PTP standard, which originally had been published in 2002 with its version 1, and in 2008 with version 2, will also receive an update. And the guys learned from their previous step when they released version 2, it was not backward compatible to version 1. So now they have learned, and whatever will be contained in 2020 version will be named version 2.1 and will not break the backward compatibility. So that means that everything the standard contains are additions which are fully backward compatible, or put it the other way around, any equipment which is currently working under version 2 will continue to work under this standard as well. So they are preserving the widespread ecosystem. So finally, we have another organization, which is the Joint Task Force on Network Media. That is a group which is supported by the EMVA, the European Broadcast Union, the SMPTE, and the Video Services Forum. And those guys are more on the user side of things. So the JTNM has gathered user requirements, has evaluated those user requirements, and with user I mean large broadcasting organizations and their application requirements. And they have generated a reference architecture and a roadmap. The roadmap is an important tool which is also updated twice a year. And this JTM Roadmap looks like this. It is lining up the different technology layers which are required to build full systems, and it has a time axis. So on the bottom layer there's the current SDI transport standard. That's major technology. There's also SDI over IP as defined in 2022-6. Major technology, that's existing. The next step would be elementary streams as defined by 2110. So they have a more flexible and efficient workflow opportunity. New formats can easily be supported. And also, as it's called here, mezzanine compression. That's the transport layer. Then to build systems, we also need to have a network and resource management layer. So a control layer, management layer, which actually brings devices together, basically builds the foundation of control and management operation. Knows at the end what devices are on the network, what streams are currently flowing, so everything which is on top of the pure transport realm. And then further upwards, there are layers which deal with dematerialized facilities. Nice word creation. So that's everything which is in virtual environment, all the way up to cloud fit operations, so that you not have to run your video studio in a real world environment anymore, but you can move it onwards to, let's say, an Amazon cloud service. You just insert your credit card, you get a production station for the next 14 days, and once you don't use it anymore, it's just teared down, virtual in the cloud. So, and JTNM deals with all these levels and is putting out recommendations. And while we have 2110 and AES67 sitting there on the third level from the bottom, we also have the AMBER addressing all the upper layer functionality like network management, device management, system management through the network media open specifications. So what are the network media open specifications? It's a group within the AMBER that the AMBER is supported by a large number of industry participants. They are setting forth a number of specifications which are complementary and coexist with 2110 and AES67, as I said, to address upper layer functionality. So just briefly skip over this. The scope of the work covers identity of devices or flows in the network, timing and synchronization, discovery and registration of resources, and another lineup of functionality which is not covered by 2110 but is typically needed in fully operational environments. Not running you through the details in this presentation. I have other presentations. One is actually coming up tomorrow afternoon at I guess 2:15, one of the last sessions in the conference program, where I will go into detail on the whole NMOS side of things and what NMOS means for audio. Here's just a lineup of the interface specifications, that's what they call it, so that you just have seen it. If you want to dig deeper, all this is covered by the link which is in the back of the booth. Finally, the EBU, together with the JTNM, has issued technical recommendations on what media nodes need to provide in terms of services so that they can transport, can be synchronized, can be discovered, configured and managed, and what security measurements should be provided by nodes in order to nicely build operating systems. This is a very interesting document as well, and we see manufacturers already lining up toward these requirements. So final slide before I take too much of Aki's time, I guess. So let's skip over the summary lineup here. The last slide is what I call the overview, the power of collaboration, which gives the overview how all these groups and how all these standards come together into a working environment. So we have user requirements gathered by EBU and VSF. The user requirements are forwarded to the JTNM, which is built by EMMA, EBU, SMPTE, and VSF. They have generated a reference architecture out of that, which has been taken by the Video Services Forum. And the Video Services Forum was producing technical recommendations based on these inputs, and they have been given to SMPTE as the basis for the 2110 suite of standards. Now, of course, we also need the input of other standardization organizations like IEEE, for example, for Ethernet and for the P2P protocol, SMPTE 2059, IETF, the Internet Engineering Task Force, which deals with IP protocols like RTP, and AES67, of course. All these have contributed into the VSF technical recommendations 03 and 04. Then there's this AIMS group. This is what you mostly see here. The AIMS is a market-based advocacy and feedback group. So it's an interest group which is basically there to help the standard organizations to get the requirements in place, to foster the adoption, to also educate the industry. That's what we are doing here. Educate the industry about all these standards and, you know, prove the basis, flatten the basis for IP, further IP adoption. The user requirements have also been taken up by AMWA, and they are flowing into the AMWA NMOS specifications, and the output of the SMPTE is the 2110 document. And here at the end, we have the synergy of SMPTE 2110 specifications and the AMWA NMOS specifications on which we can build fully working systems. So that is how all these industry organizations relate to each other and how they basically contribute to the final working end product, to the architecture, to the whole layout. That's it from my side. Just giving you the overview of what's going on in the industry with the standards and how they all relate to each other. If you have any further questions at the moment, feel free to ask. Otherwise, we will be around. No questions? No, I know it's a complex and dry topic, but it might help to, you know, sort out all these different names which are flowing around. And I'm here for the next hour, and I hand it over to, I guess, Aki, right? You're next. Okay, so please stay here for Aki from Genel.